So let's begin. Our next speaker is Shrivastava. Thank you.
Thank you for inviting. This has been great so far. So I'll talk about some of my recent work that I've been doing in hashing and adaptive sampling. So this is joint work with my group of PhD students, masters and undergrads. I'm Anshumali Shrivastava. I work at Rice University as I'm an assistant professor there. All right. So this is a slide from Michael Mahoney's talk where in randomized numerical linear algebra, one of the basic pillars is sampling. So you sample the data in some carefully data-dependent manner to reduce the size of the size of the data, and then do computation on this reduced matrix. But what I will focus on in many scenarios, and especially in very large-scale machine learning and signal processing application, the sampling itself is the computational bottleneck. And if you're thinking how, here is a teaser motivation. So, a classical example of stochastic gradient descent. So you don't want to compute a full gradient because it's too expensive. So you randomly sample a point and compute the gradient only on that point, and that's an unbiased estimate of a gradient, and you use this for your descent. Now there has been this question in the literature: are there better estimates? And if you're aware of lever source sampling and other adaptive sampling, the answer is of course yes. You should actually pick some Wi. You should pick xi in proportion to some Wi, which is the weight, which is actually some sort of an L2 norm of the gradient. So ideally, you should pick a data which has maximum impact at this point for your gradient descent. So think of this as a sum, right? Ideally, you want to pick the heavier entries of the sum if you want to estimate a sum. As simple as that. Now, so that's great, but how will you do it? Because every time, whenever you make a gradient step, your parameter changes, and so does these weights. So if you think about it, just computing these weights are order n operation, you are better off computing the full gradient rather than estimating it. So this is some sort of a chicken and the egg loop. And what I'm going to talk about is that there are ways in which we can reduce this chicken and the egg loop with having something like a constant amortized cost. So here is the outline of the talk. I'll talk about the classical LSH algorithm, and I'll introduce what it is and how by just mere indexing we can do something much better than random. And then I'll show that we can use this LSH algorithm, which is classically used for sublinear near neighbor search, for an estimation problem, and even similar, an adaptive sampling in deep neural network, which can actually increase the computation further. Then I'll just highlight some of the other projects that I'm interested in case you have any questions. Okay. So when I say hashing, yes, you're right. If you're thinking about Java hash map, so what is a hash function? A hash function, it just takes a data object of interest. So for example, a vector in R to the power d, and it maps this object to a discrete set. So that's what a hash function is. And ideally in literature, you want if x is equal to y, then its hash value should be equal to, h of x should be equal to h of y. And if they are not, then you don't want them to be equal. That's the ideal hash function. And if you're thinking of Java hash map, this is what it is used for. There is a usual interview question is that given an array of integers, n integers, you want to remove duplicates. If you try comparison, it's n square. If you try sorting, it's n log n. But if you use hashing, it's big O n. So somehow this accessing a memory location, the pointer thing, accessing a memory location is a constant time operation. This is the whole reason of the use of data structure, and it makes something much better than what you would have imagined. Now, this probabilistic hashing is also a hash function, except that there are some coins in the hash function, and I'll show you what I mean by those coins. But again, the same thing. It takes the data object and maps to a discrete set. Okay? And this time, I relax the definition in a probabilistic way. So instead of wanting x equal to y and h of x equal to h of y, I'll say if similarity of x and y is high, then I want the probability of the agreement of the hash value to be high. If the similarity is low, then what I want is that the probability of hash agreement is low. So this is a definition. This is a not the formal definition, but I want to give you a notion of what. So that's called a locality sensitive hashing or a locality sensitive property. And a lot is known about such hash functions. But basically what it is saying is that if I have a data point like this in which these 2 points are close and this is far, then under such a mapping, I will likely see this configuration, and it is very unlikely I will see this configuration. And now you might be wondering what this randomization is. So here is a classical example which is known as signed random projection. So basically this is how it works. So imagine we have 4 points in the space, green, orange, blue, and black. Then I randomly sample a hyperplane passing through origin. So that's where the randomness comes in the picture. And the hash value is simply which side of hyperplane the points are. So these two gets hash value 1 and these two get hash value 0. Now it's not very difficult, at least in 2 dimension, to see that if 2 points are very close in their angle, then no matter how you sample, they will always have the same hash value. And in fact, you can formally show that in the higher dimension, that the probability of agreement of the hash value is a monotonic function of what is known as cosine similarity. That means if the cosine similarity is high, the probability of agreement is high, and if the cosine similarity is low, the probability of agreement is low. And so this is a classical example of a locality sensitive hash function. And this work comes from a classical result of Gomans-Williamson, 95. All right, and this is 2 decades of work has been gone in this, and there are many popular measures that we know exist. So by measure, I mean those similarity that I showed. So we know how to construct hash function for Jaccard similarity, cosine similarity, Euclidean distance, earth mover distance, and in fact, recently we have also shown that it's possible, even when you have inner products, it is possible to construct such hash functions. So what is the use case of this hash function? And again, I have given you a hint. It's about indexing. So, you are given a query and a giant collection. So we are planning to do sublinear near-neighbor search. The problem is simple. A giant collection is given. I have a query. I want to search this collection for something closest to the query. And of course, the worst case is not very hard. It's linear, but the querying is a frequent operation and n is huge. So we want something like a sublinear time algorithm. And here is what the idea is. So let's say I have access to this magical hash function with this property, that the probability of agreement is some sort of an indicator of high similarity. Then this is what you can do. So let's say this is your data point is, and in the illustration, I'm using 2 independent hash functions. So this could be 2 sampled hyperplanes. And let's say the hash value is only 0, 1, 2, 3, 4. So I'll pick this orange point, compute h1 and h2 on this. Let's say h1 turns out to be 0, 0, and h2 turns out to be 0, 1. Then I'll take this orange point and place it at a bucket location 0, 0, 0, 1. And similarly, I'll do it for all the points. Now let's say I get a query, then I'll use the same 2 hash function and compute. So let's say h1 of query comes out to be 1, 1, and h2 of query is 0, 1. Now instead of treating every object in this database as a candidate, the argument is, let me just go to the bucket indexed by 1101 and look for candidates there. Now the argument is that it's a good bucket. Why? Because every element in that bucket has h1 equal to 1, 1 and h2 equal to 0, 1. So just by a bucket probe, assuming my hash function computations are fast, just by a bucket probe, I'm guaranteed to find data points which has agreed on the hash value at least twice in this case. And so I'm beating randomness just by a bucket lookup. And if you know how the arguments of boosting work, this is essentially sufficient, and in fact this argument can be boosted. So basically in this case 2 is just an illustration. I can have k of them, and to not miss probabilistically the points, I can repeat the process L times. So instead of probing 1 bucket, I'm probing some L number of buckets in L independent hash table and looking at the union of the buckets as my candidate set. And basically the theory says that there is a sweet spot, and so if you're smart about tuning this K and L, you can solve a very particular instance of a search problem which is called C approximate search, and that is a classical result from Indek and Motwani from 98. So this is, the LSH has been a hugely successful, like algorithm in both, industry and academia. There are similarity search related problems have been solved. You can do dimensionality reduction, you can do similarity estimation, and many other problems. And in fact, it won the 2012 ACM Paris Canaclis Theory and Practice Award. And what we are going to ask is, are there other fundamental problems that we can solve with this technique? Okay. And I have essentially given you the hint. So basically what is happening is I take a data, I have a query, I compute some hash of a query, go to a bucket, and I'm beating randomness. In fact, if you look at the proofs of LSH, here is what it looks like. That given a query Q, and if I have K and L parameters as shown in this picture, then what is happening is I'm retrieving any date X from the data set with precisely this probability. And what is this probability? This is the collision probability. Raised to K is the probability of finding that element in the bucket. 1 minus that is not finding in one hash table. Raised to L is not finding in any hash table, and 1 minus that is finding. So you not only know that it is sampled, you have retrieved a point X, but you also know what is the probability of retrieval. And in fact, this function is a monotonic function of the similarity, which means that given a query, I will retrieve X1 with higher probability compared to X2 if and only if the similarity of x1 with the query is higher than x2. And not only that, I also know the probability expression. To me, this is huge. I am sampling something from a data structure. I know the probability of sampling, and I know it's adaptive. And I can do just by mere bucket lookup. So, we could do a lot of things here. So again, like if you look at, so LSH is considered a black box for search, but I think search is just one among the possibility, because what we are doing is adaptive sampling. We are solving a very, a very fundamental problem here. So here is another motivating problem. So log linear models is hugely popular, like word-to-vec application, in which the probability of a class y given a context x and parameters theta is modeled as e to the power the parameter corresponding to the class times x divided by a partition function. Now this partition function is just a sum over all possible classes. Now if you're thinking about word-to-vec, this is a summation over billions. You need partition function both for inference and computing the gradient. So this is an expensive operation. So you want to estimate this partition function without doing a lot of work. And there has been a lot of work around it. So one thing is, okay, it's a summation. So summation can be approximated by expectation. So if you could sample the classes in proportion to this probability, then you just take few samples, add them up, you're done. But hang on for a second, how do I sample with this quantity? Because this quantity itself, first I have to compute the weights and sample. So that beats the whole purpose, because we want to beat linearity, and this is linear to just even know the weights. And the weights change with context. So that's another issue. So, well, the literature says, okay, if you cannot sample from here, there's something called importance sampling. So you sample from some proposal G, and then adjust your weight so that you still get an unbiased estimator. But again, there is some sort of a chicken and an egg loop. It doesn't quite work unless G is close to F. So here is the dilemma. I want to sample from F. I cannot, so I go to a proxy, but the proxy should be as good as the original to get anything interesting. And then basically there's no efficient choice in literature, so what people do is random sampling in practice. But imagine you have this as a power law and you are doing a random sampling, it's going to be a very bad estimate, where power law is common in word-to-vec kind of scenarios. So again, like as I mentioned, here's what we are going to do. We are going to take all these theta y's and put them into the hash table, and whenever a current context arrives, I'm going to probe few buckets and sample from the bucket, and then since I know the probability of the sampling, I should be able to construct an estimator. Now there is some caution here, is that the samples are correlated and non-normalized, so it's not quite important sampling. But that doesn't stop us. If you know how expectation works, expectation doesn't worry anything about, you can just, know the probability of sampling, you know what you're sampling, so you can actually construct an unbiased estimator. So basically you you pre-process, so you pay one-time cost of pre-processing your parameters into the hash table. Then given the context, you go to few buckets, get some elements from there, and you construct this estimator. Now you can show that this is unbiased, it's simple. The variance looks something like this. So this variance is like a random sampling variance, and this is because of the correlations in LSH. But if you look at this term, it says that if a randomly sampled pair is likely to be in the same bucket, then this quantity will be positive, otherwise it will be negative. So this is a very big negative term, so we are going to get better variance than random sampling. And it's also not very difficult. I have a sum which has heavy entries and not so heavy entries, and the probability of retrieving heavier entries is more than the probability of entering not so heavy entries, so I should get better estimators. So in fact, if you're using a hash function for inner products, so remember this thing is monotonic in inner product. So if I have a hash function where the sampling is monotonic in inner product, I am guaranteed that if the optimal sampling prefers x1 over x2, then so does my sampling. And basically the modes are the same, and you can get an efficient estimation. How does it work? So this is two data set, which is basically you are doing the word-to-vec kind of thing. And this is pen, tree, bank, and text state data set with like 1 million and 100 million words. So what you are trying to do is we are fitting a language model, and we are measuring the goodness of fit using what is known as the perplexity. And this is a snapshot of what happens in between. So what we are doing is we are estimating the partition function using uniform sampling. This is what it is. Uniform sampling is very fast. Think about it. Flip a coin, pick an element. What can beat that? Now LSH sampling is also very fast. You can see roughly same cost as uniform sampling. You are computing a hash function like a sparse hash functions, going to a bucket, picking few points from there. That's also roughly as fast. It has much better accuracy than random sampling. So here is the number of samples, and here is the mean average estimator. Now there are two other methods which I have put in dotted based on the Max Gumbel trick, and using efficient LSH for those tricks. But those tricks are like horribly expensive. You can see the amount of time it requires for estimation, and if you do approximation, it even diverges. Now uniform is slightly faster than LSH, but you can see that in terms of the perplexity, it has a very bad, because of the bad estimation, it gives bad perplexity. Whereas LSH almost comes close to the standard, which is the gold standard, what we are looking at. But what I want you to focus on this, and this is random sampling and this is LSH sampling. So again, so here is something to note about. A lot of people say that, oh, we could use near neighbor search. So for near neighbor search, you have to construct many buckets. If you know the theory of LSH, you have to construct several buckets, take a candidate set, do a candidate filtering, and get the top K. You're doing a lot of work in candidate filtering. You could have utilized that. But again, you need a lot of hash tables. Now for sampling, even one table will work, because one table is still beating randomness. Now there's an interesting trade-off of how many tables you want to use and how much you want to beat randomness, but there is a whole knob of computation versus accuracy there. So that's why sampling is way more efficient, and that is why you can see this speed. Otherwise, if you are not, then it won't.
How many tables are you using?
Here I think we are using 10 or 15 tables, or even less than that. And here is this thing. And for SGD, we just use one table or something. It still works. So again, remember I told you this application. I have to estimate the gradient using one random sample, or what I can do is use some sort of LSH. So remember, the optimal variance sampling is some sort of a L2 norm of the gradient. Now for linear regression, this L2 norm resolves something like this. Now if you think about this, this is a data, this term depends on the data, and this depends on the parameter which changes. So what I can do is I can throw this thing, which is more or less fixed, into the hash table, and every time with the parameter I query the hash table, get a sample from the bucket, and divide it by the sampling probability. And if you're smart about what hash functions you are using, your per cost is roughly 1.5 times the cost of SGD. So here is one experiment of how good the gradients are. So on the y-axis is the cosine similarity of the true gradient with the estimated gradient. An estimation being random or LSH based. Random is blue, LSH based is red. So you're getting better, and this is the number of samples. So number of sample reduces the variance. So you're seeing that you're constantly getting better estimates of the gradient. And what does it translate into this? So what is going on here? Left is an algorithm called AdaGrad. The right is the algorithm called SGD. The only thing that has changed is the gradient estimate. So I say that, oh, choose your favorite gradient descent algorithm, Adam, AdaGrad. Now you will use a random sample to estimate a gradient. I'll give you LSH based gradient. So the only thing that has changed is the gradient. The blue is the random sampling based gradient, and the red is the LSH based gradient. Now the dotted is test and the bold is train. And this is the running time, and this is the epoch. So epoch wise, you're beating in convergence. It's fine because you're getting better estimate. But epoch wise convergence is not impressive, because I could use Newtons to get epoch wise convergence. But I'm also getting roughly similar kind of convergent behavior even in running time. And that is because I'm only paying 1.5 times the cost of SGD. So my update cost is roughly 1.5 times. And remember, SGD is fast. You flip a coin, pick a sample, do your update. Beating that is hard. So again, so basically what fundamental problem that we attack is if you are given some sort of a time evolving weights and you want to, yes?
Could you go to what problem are you solving here?
Oh, linear regression, sorry. So given n time evolving weights, I want to sample every time in proportion to these weights. If these weights has a very specific form, very specific, then I think the sampling is efficient. Okay, so till now what we have been doing is there was a fixed part which was data. We hash it in the hash table, took at the context or the parameter and sample. Now we'll turn the tables around, and the motivation is we want to do large scale neural networks. So again, this phenomena is familiar with everyone. We need larger networks and larger data size to achieve better accuracy. And of course, there's tons of engineering and backpropagation. Now, we have started getting more and more ambitious. We want neural networks to predict everything. Now, basic information theory says that if I have a model that has information about almost everything, it cannot be small. And therefore, neural network sizes are growing. And it's not surprising that last year Google reported a 137 billion parameter neural network, which was called one model for all. It does text, images, and speech all together. Now, backpropagation, as you know, there is a consensus among the field that the current backpropagation is not sustainable because of it has slow training and validation, it stalls the scientific process, it requires expensive clusters, not everybody can use it. The memory and energy are out of bounds for IoT applications, and it's too slow for latency critical applications. So if you're predicting click and a very large network is passing through it, it's not happening in a few milliseconds, even with the kind of computation power we have. So there are a lot of other approaches, but one thing that is there is, so imagine I have a billion neurons network or billion parameter network, and I'm only showing an image of a cat. Is it going to change my belief about all the parameters? The answer is no. If it's changing the belief, that means my whole learning is like, somehow, so ideally it only changes the parameters that is relevant to this input. So it's essentially becoming a search and an adaptive sampling problem in disguise. And in fact, there was a work in MIPS 2014 that shows that in a neural network with input layer and a hidden layer, and the activation is a monotonic function of the inner product, what they did was they took every data point, compute all the activation, and only pick very few neurons based on some sort of a Bernoulli sampling, and did feed forward and backpropagation only on those neurons. So basically, you take a very sparse snapshot of a network based on some sort of a sampling, and they show that this leads to better generalization. But computationally, it's not very lucrative because it does the full cost of training and testing. So first you compute all the activation, you have done all the work, then you do the sampling, and then sparsify the network for training and testing. Now again, since from the context of the talk, this is what we are going to do. So this time,
that sparsification depends on the X.
Yes.
With different sparsification, different X.
Yes, so that's one. So this is very different. So thanks for that. This is very different. So it's not like I'm sparsifying a network. Every input picks a different set of neurons. So a cat will pick cat neurons, a car will pick car neurons. And that's sufficient for training and testing, and not just sufficient, it's even better for generalization. So here is how we are going to make this efficient. So we know that we are going to sample, but instead of using a Bernoulli sampling, I'm going to replace it with a very unusual distribution. But what is, so here is, let's say I have this original neural network. I take this layer, throw all the neurons into the hash tables. Similarly, I do it at every layer. So this time I'm not hashing data, I'm hashing neurons into the hash table. Neurons are just weight vectors. Now let's say I get an input, then I hash the input and go to certain bucket and only pick the nodes that are there in those bucket. And these are just pointers. So basically I get to know, just by a few bucket lookups, I know the sparsity pattern of the network. And what I will do is I will only feed forward on this and backpropagate. And then once I have backpropagated, I will update the weights in the hash tables. So my order of computation, the complexity of computation, is the order of the active neurons rather than the total number of parameters. And if you believe that the networks can go very sparse and the number of neurons can be much less than the total, the total size of the network, then it's going to be very efficient. So here's what some plots are. So these are 4 different data sets. On the x-axis is what is the fraction of neurons that are active, or the fraction of parameters that I'm using in every SGD, backpropagation epoch. The black line is the neural network, fully connected neural network. This is 2 fully connected layers, 1,000 nodes in each layer. The 2 dotted lines are the expensive method, which is using the sampling idea. So they compute all the activation to do Bernoulli sampling and stuff. The pink line is random sampling. I don't care about any adaptiveness. I'll randomly pick neurons. It's efficient, but it doesn't lead to good accuracy. And the blue line is the LSH-based sampling. Now this pink line at 50% becomes dropout, because that's what dropout is. But then what you can see is we can even work with 5 or 10% sparsity in a 1,000-layer neuron and get roughly the same accuracy as the original network. And as the network goes bigger, for example, if I have 1 million or 1 billion layers, then it's even more efficient because I just need only few.
So for this example, I just got confused what we were hashing. We hashed the weight vectors for each neuron.
Yes.
And then what's our distance function?
I'm using inner product hashing. So my distance function is just inner product, and I know that activations are monotonic in inner product.
Okay.
So I want to pick large activation, as in I want to pick large inner products, and that is what I'm doing.
But then you're doing this just with like the input.
So, no, so this is going to the hash tables, the neurons,
yeah.
And the input is the query time.
Yeah.
So basically, I hash this, I go here, then I get a sparse representation here. I hash that sparse representation, goes to the next layer, and so on and so forth.
Oh, so you're doing this multi-layer.
Oh, multi-layer. So every layer has a hash table. I'm sorry, I
it's
sped
okay.
up. Yeah.
And just because it's monotonic, it makes sense to do an inner product.
Yes. Yes.
Yeah.
And this is what the results look like. So I can.
Basic question: inner product with a random vector or what?
No, inner product, so the hash function is catering the inner product similarity.
Yes.
So I'm guaranteed that if there is a hash agreement, then the inner product will be higher. And based on that, I can create a hash tables. So now this is good. So I can make the networks very sparse, right? So I can make the network very sparse, the computations are less. Now there's a bonus here. It's asynchronous parallelism. So if imagine I have a cat input and a car input, and they are activating a very sparse set of neurons, they are unlikely to overlap. So I can basically do SGD in parallel. I think we had a talk that shows that we need smaller batch size, and the parallelism these days is just based on the batch size because of the matrix multiplication. Here I'm going away from matrix multiplication and talking about hash tables. Now hash tables are something which databases people have mastered over 2 decades. It's efficient, this algorithm is efficient, and plus it's parallelizable in the number of inputs. So as you get more and more inputs, so this is basically shows the convergence with 1 thread, 8 thread, and 56 threads, all doing asynchronous gradient descent without any synchronization. And you can see the running time goes straight down with the number of processors, but the convergence is not affected. But if you do the dense, I also have those plots in the paper that the convergence is affected if you do dense.
So when you're talking about accuracy, are you comparing this to ground truth or to the best you could do if you train the whole network?
So this accuracy plot is with respect to the best you can do with the network.
With the network? Okay.
Yeah, but there is something weird here. Sometimes with randomization, you even...
Weird. I would suspect this is a regularization effect.
Exactly, and that is what I was very interested about Mike's talk, because we could actually test this and see if this is a regularization, which I suspect is a regularization.
It's because of the sparse.
Yeah, and it's also random regularization. Yes, that's very exciting. So you see this phenomena, right? And you see this often actually. So yeah, and so that's so there are other projects that I'm involved with. I have been using like sketching algorithms for K-class classification. Like extreme classification is log memory, so you can actually sketch the classes. We can do feature selection using count sketches in log D memory. Then we had a recent paper in MIPS which is talk about how we can reduce the heaps. How we can avoid using heaps in distributed computing. So count sketches, if you want to get the top K, you need a heap data structure, and that creates some problem when you are merging across threads. So we can get rid of that. And then recently I'm also very excited about, so now once you go to a bucket, you sample, you also know the probability. I think we can design efficient proposals for Bayesian estimation using hashing. So these are all the projects I'm interested in. Here is a quick peek on how we do large-scale feature selection. So imagine you're doing a regression, and you cannot afford a memory which is of the order of the dimension. So imagine this is the application was DNA datasets. You have like hundreds of billions of dimensions. So that's like a terabyte of data just to store a weight vector. So you can afford sparsity, but you cannot afford a dense vector. So if you take an example is just a sequence. So it's very small, it's very sparse. So SGD is possible, but at any point of time you cannot, if it starts becoming dense, you have to threshold or do something else. Here is a better way to do it. You start with a count sketch. The gradient descent is a linear operator, and sketching is linear. So sum of sketches is sketches of sum. So basically every time you get a gradient, you push it to the sketch, and to get the parameter, you just query the sketch. And the sketch could be any compressed sensing structure, but count sketches are nice because they have like very fast update and query time. We actually showed we could do a feature selection on 2.3 billion dimensions, and it was much better than hard thresholding based approaches, which is the only other thing we could try on that data set. So these are the kind of stuff that I'm interested in. In this talk, I mainly focused on computations, but there are a whole spectrum of work based on memory, which I won't have time to go into it, but I'll be happy to talk otherwise. Here are the references that are associated with what I said. And I will conclude that this is a perfect time for algorithmic disruption in large-scale machine learning, because it's kind of a consensus that the current techniques are not sustainable, especially when it comes to deep learning. And I think if you revisit old algorithm with a new perspective, then there are a lot of hopes. And again, probabilistic hashing and randomization is a great tool, and that's why this is also a great workshop. Thank you.
Questions?
Back to the neural network. If you kind of drop neurons in the way you said, in training, do you end up with a sparser network? With a sparser set of final trained weights?
So what you're saying is you drop completely the neurons.
No, you train, say I didn't know this trick, and I just train my network, and it's like dense with all W's being non-zeros.
Right.
And then you do this trick, and you have a different W's. Are your W's sparser than my W's, or not?
We haven't tested that part, yeah. But I think it's interesting. One thing we could do is take a network, trained network, and then fine-tune it using this approach to make the inference efficient, because this also makes inference efficient.
So compare in time against Algebra.
So here this is. So this is I'm not comparing against Adagrad. So I'm asking, okay, you have your favorite gradient descent algorithm, whatever it is, give it to me. And the only thing I'll change is your gradient descent algorithm will use a random sample to estimate the gradient. I will use LSS sample to estimate the gradient. So you think of a gradient estimator as an oracle. Generally people use random sampling. I'll use LSS sampler. Okay. And the plots here is this is Adagrad algorithm and this is SGD algorithm.
Okay, and that's Adagrad with the sampling that you provide.
Yeah, so the blue line is the usual Adagrad which uses random sample, and then the red line is the Adagrad that uses the oracle which uses LSH. So the only thing that has changed in the two algorithm is just the oracle. So this I think is also a fair comparison, because we are not, because these things are very sensitive to a whole bunch of things.
Just one short question. I don't know if anyone else. The regularization effect that you observe, does it depend on the number of tables or hash tables you have?
No, so the way we do it right now is because if you just use one hash table, it's kind of not enough randomization. So what you do actually is you have a whole bunch of hash tables. Then during the runtime, you randomly pick few hash tables and take buckets from there. So this way you mix enough, especially in the SGD, because otherwise once you create a hash table, you will get biased. Obviously in theory it doesn't matter because you flip the coin before or later, it's fine. But in practice, the structure is decided based on tables. So right now we had let's say 20 tables, and during query time we randomly go to one of the hash table and pick a bucket from there. So but I think that's an interesting question, is that how it depends on the hash tables.
Okay, thank you.